Hi guys, in this video we're going to cover regression trees. Regression trees is a technique that was developed in the 80s along with classification trees. And you might recognize the algorithm CART, which stands for Classification and Regression Trees. So what these two techniques rolled up into this acronym have in common is they're based on a tree model. Sometimes you can just express that in rules. So what I want to do here is focus on just the regression tree part of this CART. And I want to use Excel not because that is the preferred tool for machine learning and regression trees, but that it's a good way to explain the basic fundamental concepts of these algorithms. So here we're going to start by talking about our data set. Here I have this very tiny little data set which is sufficient for us to just understand the concepts of a regression tree. So here you see I have three features or three variables, and they have some context. It seems to be some students' information or attributes. So let's just go through it. We have tutorials. I have my students watch tutorials. So I have categorized the student as to whether they watched all of the tutorials or just some of the tutorials. Next feature, labs. That's I give lab assignments in my courses. So I have categorized the student into the category of whether they completed the lab or they only partially completed labs. And finally I have their, let's say, final exam score. Okay, so each one of these rows is an example of a student, and I have here, if we just count these up, glance at our little preview here in the bottom corner, I have 15 students here. Okay, so I have 15 examples, 3 features. One of them happens to be the one I want to predict. So I am here showing an example of a supervised learning technique because we have a target feature, namely exam, which we want to predict. Clearly this is a quantitative feature, a numeric feature, so clearly we're going to that's going to limit the techniques that we can use, the machine learning techniques. So the regression trees happens to be one of those techniques. So in this video we're going to approach this problem with a regression tree. Okay, great. Having understood our data set, and let's again pretend that this is our training data. So let's say we've already split our data into a test and training set. We've set the test set aside. We don't see it here. This is our training data. We have 15 examples, and we're going to try to apply a regression tree onto this data. So first thing is to start understanding the basic concepts of regression trees. Trees in general use a divide and conquer strategy to try to divide the training data into smaller and smaller subsets that are purer and purer, or more and more homogeneous. So how does it do that? Well, basically what an algorithm will do is go through each of the available predictors. So in this case I have 2 predictors here, at least 2 potential predictors, so very tiny example. I could have upwards of 100 plus predictors. So the algorithm will go through all the predictors and see which one of them is the most predictive of the target feature. And that feature will be the root of our tree. So if you can imagine one of these trees, hopefully you've seen one of these before, it's almost like an upside down tree. So you have the root at the top, and then you have splits, and then you have nodes. These are all nodes. You have different types of nodes. We have the root node, obviously, at the very root. Then we have decision nodes along the way, and these are sometimes ending early and sometimes they continue on, and when the tree terminates we call that a terminal node. So, or a leaf. So this is a leaf, that's a leaf, that's a leaf, that's a leaf, and this guy happens to be a leaf as well. So this is an example of what a tree looks like when you kind of plot it out. So what we're trying to find here is the first kind of decision in this tree, the root of this tree. So since there's only two features to choose from, this tree will never grow to as large as what I've drawn out here, but we're going to basically be able to understand how the algorithms work to build these trees. If we can understand how it makes the first decision, we can then extrapolate that and induce how the rest of the decisions are made. Although there's a lot of computing that goes into this, this is definitely not something anyone would want to do by hand, except once in a tutorial like this to understand the fundamentals. Okay, so let's go forward. How does the algorithm decide which of these two is the most predictive of our target feature? Well, specifically, it's going to choose the feature, either tutorials or labs, that creates the purest subgroups. So, when we have a numerical feature, a pure subgroup can be measured by the standard deviation, by the variance, or by the sum of squares, or absolute deviation. Those are all plausible ways of measuring the purity of the resulting subgroups. So what I'm going to use here is standard deviation. It's as good as any other choice as our measure of purity. So let's go forward. So what we basically have to do is mimic what the algorithm would do. First, it would choose one of these features. So we're going to pick tutorials first. And it would look at how many levels tutorials has. So we see clearly, based on present evidence, that there's a level called sum and a level called all. So there's basically a binary feature here. So it's going to split this entire training data into two subgroups. One, which only includes tutorials equals sum, and the other includes tutorials equals all. And then we're going to grab all the exam scores for each of those groups and measure the standard deviation of the result. So let's do that. But before we jump in, it's good to have a benchmark measurement of what the standard deviation was before we started to split the data into subgroups or subsets. So let's calculate that on the side. So we can do a little standard deviation. Let's call this data set the segment or subset capital S. So that's before we did any splitting. So standard deviation of our target feature happens to be 24.51. Let's just hide a couple decimal places here. Okay? Now we're going to split based on tutorials and see what the resulting standard deviations are. So let's kind of use some Excel skills to help us out in this process. I'm going to actually use a pivot table. So I'm going to highlight my data, insert, pivot table. I'm going to put it in the existing sheet. I'm going to squeeze it right here. Okay. And now I'm going to build this tree. I'm going to put tutorials on the rows and exam score and the values. By default, you can see we get the sum of exam scores. Instead of the sum, why don't we see if Excel can directly calculate the standard deviation? So actually, let me pull back. What are these numbers? So you understand this one time before I go forward, because I'm going to repeat this for labs as well. This number 418 is the sum of the exams for the tutorials being all. So this exam score, all the ones I'm underlying, where the tutorials equals all. So the sum of these 1, 2, 3, 4, 5, 6 exam scores is 418. And for sum, tutorials equals sum, S-O-M-E, the sum is 266. That's what we're looking at here. So I'm not directly interested in that, but I can change that sum to another calculation by going to the drop-down value field settings, scroll down, and I see I have standard deviation here. Click OK, and we have the standard deviations. I can reduce these a lot. In fact, we don't want the grand total either, so we can go to design, grand totals, just turn them off. Okay, so this was for tutorials. These are the resulting standard deviations for the tutorials, the split based on tutorials. Okay, so we see that the standard deviation of exam scores for students who watched all the tutorials is quite low. And for some, it's considerably higher. Okay, but definitely both of these are less than the standard deviation of the original segment, which I labeled S, which was the entire training data set. Okay? Okay, great. Now, we have to have a way to combine these two numbers into one measure of standard deviation that resulted from splitting the data on the categories of this feature. So the way we do that is actually, you would think you can average them. You're basically thinking the right thing. The only thing I would add is you should average them, but you should give more weight to the standard deviation that came from the bigger subset. So what do I mean? There was 15 original examples. Those 15 got split into these two groups. These are the resulting standard deviations of those two groups. So let's find out how many observations came into each of these groups. So one quick way we can do that is actually we can use the pivot table again. So we can drag exams in again. And again, it gives me the sum, but I don't want the sum. I want the count. So I can ask for the count. Okay, so I have let me center these, get this a little prettier. All right, so I have the standard deviations for the subgroups and the count. So clearly, look, we only had 6 students who completed all the tutorials, but 9 that completed just some. This should total 15, right? And it does. Now, using these counts, I'm going to get a weighted average for the standard deviation from tutorials. So how do I do that? Well, first off, let me maybe label standard deviation for tutorials. And I'm going to calculate that maybe right here. So this is going to just be a weighted average, right? It's going to be this guy times, in parentheses, this guy divided by 15. I know this formula looks really messy because when you reference cells in a pivot table, it just looks ugly. But all I'm doing here is, here, let me start over to just show you. I'm just taking this number and multiplying it by that number divided by 15. In other words, the proportion of values that came from that, that had all. And then I'm adding that to this standard deviation times, and in parentheses, this number over 15, which is the proportion of all. Okay? And then let's hit enter, and we get the standard deviation for the split on tutorials. Okay, so 13.06. So we've reduced the standard deviation quite a bit, as you can see. We started with 24.51. If we split based on tutorials, the standard deviation is now 13. It seems like we're achieving some standard deviation reduction. And in fact, there is a way to measure how well this split performed called standard deviation reduction. So let's calculate that. So let's just make this label. Standard deviation reduction for tutorials. Let's calculate that field right here. All that's going to be, it's a very simple calculation. It's the standard deviation of the parent, which was segment S, minus the standard deviation of the children, which we combined into this number. So the children are these guys, right? This split that we created. And this is their standard deviation. We combine the standard deviation into this one number based on a weighted average using the weights. This was the standard deviation that we started with. In other words, the parent, that was the standard deviation of this entire data set. So how much was this reduced? Well, we just take this guy, the parent, minus the child. And that's what we're doing here. So we have a standard deviation reduction of 11.44. The higher that number is, the better. So we now have a measurement of how well tutorials would do in reducing the standard deviation. What's left for us to do and what the algorithm would do is now put that number aside in memory and move on to the next feature in its list. So for us, thank God, we only have one other feature. But if there was 100 more, we would have to go through 100. Okay? So we're going to do the same thing for labs now. So we're going to create the pivot table again. I'm going to go a little faster here because we just did this. Let's put it right here. We're going to throw exams in values. This time labs in rows. And we're going to change this, remember, to standard deviation, not sum. And we're going to also get the counts. And we're also going to get rid of grand totals. It's just not necessary. And we're going to do a little formatting here very quickly. Basically the same formatting I did above. Just make this look a little more aesthetically pleasing. So this is for labs. So now we can reflect on what we have. So we see there was almost a 50-50 split of students that completed the labs and left the labs partially completed. It was 8 to 7. Of course, this should add to 15, right? These were the standard deviations of the subgroups. So one more time, that number, 9.05, is the standard deviation for all completed lab exam scores. So this number, this, that should be 8 exams, 8 students. And if you get the standard deviation of the numbers that I've underlined, it will be 9.05. And then do the same for partial, 11.49. But hey, let Excel do that calculation for us. What we need to do now, these are the children. I need to combine their standard deviation into one number, which would represent the standard deviation resulting from that split, right? So let's label that the standard deviation of labs. And let's calculate that. Again, it's going to be this guy times this over 15 plus this guy times this guy over 15. And we have our number here. So we see that the standard deviation that results from splitting the training data on labs is 10.19, which is significantly less than the parent 24.51 and is less than the split from tutorials. So we see here, you might see already, that labs is doing a better job at creating purer subgroups and therefore is more predictive of exams than tutorials is. So if I were to say, which of these two, if someone would walk in and say, which of these two features is better at predicting a student's final exam score, I would conclude labs. If I know how whether you completed the labs or left them partial, I am better off at predicting your exam score than if I only knew whether you completed the tutorials or not. Okay? But that doesn't mean that that extra information is not going to make my predictions even better. In fact, it will. But if has to be a choice between which of these two is most predictive, labs seems to be the most predictive based on the fact that it's reduced the standard deviation more. But let's make it official. Let's calculate the standard deviation reduction for the split created by labs. So all that's going to be is the parent's standard deviation minus the children's, which we combined into this number using a weighted average. And we see what we already saw coming, that the standard deviation reduction was 14.33, which is much higher than, well, it's higher than 11.44. Therefore, if there was a race between tutorials and labs to see which is most predictive, we have just learned, or the algorithm has just learned, that labs is the winner. So how does this translate into a tree? Now the tree has begun to form. The root is where the tree starts, although these trees are upside down. It still starts at the root. The root of this tree, which I drew earlier, just to give you an idea what these trees look like, is now not empty anymore. It's labs. And since labs has two categories, two levels, it's binary, right? So it's going to have, no question, it's going to have two branches. One is going to be for completed labs and one is going to be for partial labs. Now the tree hasn't finished growing necessarily, it's just begun to grow. The root node is decided like this, what we just went through. Now the tree will continue to apply this same exact technique that we just did to continue growing this tree on and on and on until some stopping criteria is reached. There's a few different ways of approaching these trees. What we're trying to get after here are the fundamentals, but based on some kind of predefined size. Sometimes trees are overgrown and then pruned. These are more advanced topics. The point of this series is to actually hit the fundamentals and actually just show you what's going on in the background, because chances are when you actually apply this and start using this, you are going to let R or Python do the heavy lifting. Now at least you understand what's going on in the background and hopefully appreciate it more. Okay, so what I'm going to do in part 2 is actually now use this tree to make some predictions and then come up with some kind of performance measures, mean absolute deviation, something like this, to kind of complete this, at least get some closure on this tiny little example we have. So I hope this was helpful. Be sure to subscribe, share, like, comment, and watch my other series of tutorials on my YouTube channel on machine learning and various other topics. Till next time, have a great day.